All right, so we're going to look at this first one. We're reading the problem that there's a mean of 170, there's a standard deviation of 7.5, and then we want to find the z-score. So z-score is the value minus the mean over the standard deviation. So for us, that's 179 minus 170 over 7.5. We can simplify that into 9 over 7.5. And that's going to give us 1.20 for the z-score. Now the next part is to explain what the z-score means. So this means that Paul's height is 1.20 standard deviations above the average male height for his age. All right, so that's our explanation part for part A. All right, now if we look at part B here, Paul's height puts him at the 85th percentile among 15-year-old males. Explain what this means to someone who knows no statistics. So if he's at the 85th percentile, Paul's at the 85th percentile, that means that 85% of boys are shorter than or equal to Paul. So the 85th percentile just means if there's a graph and he's up here, that means most of the students or most of the people his age are right in this kind of like shaded area below him. All right, so that's parts A and B. Now, if we want to look at, we can look at part 2. So in this one, the computer used Miss Causey asked her students, and I'm just going to paste the image down here so we can see it a little better. All right, so for this one, Miss Causey asked her students how much time they had spent using the computer during the week. The following figure shows us cumulative frequency graph of her students' responses. At what percentile does a student who used their computer for 7 hours last week fall? So this down here is hours per week. If a student's at 7, that's right about here on the graph. So that puts the student at about, for part A, about 55th percentile. And then estimate the IQR from the graph, show your work. So if you remember, the IQR is Q3 minus Q1, and Q3 is the 75th percentile, and Q1 is the 25th percentile. So I'm going to erase what I put on this graph here. So if we're finding Q3, that's our 75th percentile. I'm going to go on this cumulative frequency graph and go over from 75. And then I'm also going to find the 25th percentile. So my 75th percentile is right about here. That's maybe at 12 hours a week. And my 25th percentile is about at 3. So my IQR is approximately 12 minus 3 hours a week. And we can go with that's about 9 hours a week for that. All right, moving on to the next one. A group of Australian students were estimating the width of their classroom in feet, and we're using the dot plot to answer these questions. So we are given a dot plot. We're given the mean, standard deviation, min, and then our 5-number summary here. Suppose we converted each student's guess from feet to meters. How would the shape of the distribution be affected? So these values right now are in feet. So if we went 1 foot and we want to get it in meters, we would have to divide by 3.28. So we're dividing here. That's our operation. All right, so they want to know what's going to change. So in part A, the shape does not change when you divide by a value. They also want to know the mean. So we would take the mean 43.70 and divide it by 3.28. The 3.28 comes from the conversion from feet to meters. Our new mean would be 13.32 meters. Our median, the middle value, would also get divided, so we'd take 42 from the chart and divide it by that conversion factor, 3.28, and that's going to give us 12.80 meters. And then our standard deviation is also going to change. It's going to be divided, so I'm taking that from the chart. 12.50 divided by our conversion factor is going to give me 3.81 meters. So these values here are all my new mean, median, standard deviation. They also want the IQR. So our previous IQR, if we calculate it real quick, we have 48 minus 35.5, which is 12.5. We want to take that and divide it by our conversion factor as well. And that's going to give us 3.81 meters for our IQR. All right, and that's all of part A. If you look at part B, we want to know the actual width of the room was 42.6 feet. Suppose we calculated the error in each student's guesses as followed. Guess minus 42.6. Find the mean and standard deviation. Justify your answers. So for part B, if we're subtracting, we want to know what happens. The mean is going to be 43.7 minus 42.6. We're just subtracting the two things. And that's going to give us 1.1 feet. The standard deviation is going to stay the same at 12.50 feet. It's not going to change even if we're subtracting. So subtracting a constant does not affect the spread. All right, so that's number 3. I'll keep going. Number 4. What the mean means. The figure below is the density curve. Trace the curve onto your paper. So we have the curve. Mark the appropriate location of the median and then explain your choice. So when you're looking at the median, it's going to be a little bit right to the main peak. So that's going to be our median. I chose this spot because about half of the area is on the left and half of the area is on the right. So if I calculated the area under the curve, it'd be a little bit split 50-50. If I'm looking at part B, I'm going to change the color so we can kind of see the difference here. Mark the location of the mean or the average. The average is going to be slightly to the right here because these higher values are going to kind of bring up the average. The distribution is skewed right. So the mean is greater than the median in this case. All right, if we move on to number 5, about horse pregnancies, bigger animals tend to carry their young longer before birth. The length of horse pregnancies from conception to birth varies according to a roughly normal distribution. Remember, that's our bell curve, with a mean of 336, standard deviation of 3, units are days, and they want us to use our rules, so think about our flip book, to answer the questions. So part A, almost all, 99.7 horse pregnancies fall in what interval of lengths? So to solve this question, I'm going to draw a curve because that would be the most helpful way for me to understand this. So if we have our normal curve at the center is 336, we have +1, +2, and +3 standard deviations, -1, -2, and -3 standard deviations. So if we want 99.7, that's all the way out to 3 standard deviations. So I need to find the values at 3 standard deviations. So if my standard deviation is 3 days, I'm just going to keep adding 336 plus 3 is 339. 342, and then 345 will be our +3, and then if you keep subtracting, 333, 330, and then 327 would be there. So for part A, our answer would be from 327 to 345 days would be our interval that most of the horse pregnancies last. For part B, what percent of horse pregnancies are longer than 339 days and show our work? So I'm going to draw a curve for this. Notice I have my mean in my middle. I'm going to put my standard deviation is equal to 3. I'm going to mark 339, and that's +1 standard deviation. And we want to know what's longer than that. So I'm going to shade everything under the curve that's above because those will be longer pregnancies. So if I'm thinking about my normal flipbook and I'm thinking about my curves, I can do a few things. I can add up these percentages. I can use a z-score. We'll do a z-score or we'll kind of look at the normal curve flipbook to get the percentages. So if we're looking at this, we have 1 standard deviation, 2 standard deviation, and 3 standard deviation. So I'm going to change colors so we can see the value between 1 and 2 standard deviations is 13.5%. Between 2 and 3 is 2.35, and greater than that is 0.15. So we want to add up 13.5, 2.35, and 0.15. And if we add those up, we get 16% as our value for what we had earlier. So if we're looking at that, we've got 16 is our value. So 16% is what we're going to look at. So 16% of pregnancies are longer than 339 days. All right, if you continue number 6, we'll look at a second problem. So use table A or technology to find each of the following for a standard normal distribution. In each case, sketch a standard normal curve and shade the area of interest. So the proportion of observations with this z-score. So we can start by just drawing the curve. Since it's a normal curve with a mean of 0 and standard deviation of 1, this is some notation we can get familiar with. We want to know between 1.77 and -2.25. So what you can do is shade the area in the curve in between these two, and that is going to kind of tell you the value there. When you look in table A for these values, you're going to get 2 values. You're going to get, for 1.77, you're going to get 0.9616, and for -2.25, you're going to get 0.0122. You want to subtract those to get the area in between, and that is about 94.94% of the data. All right, part B is a little different. The number Z, so such that 35% of all observations are greater than Z. So if we are looking in our graph, again, normal 0 and 1, we want to know what the Z value is so that 35% of observations are greater. So if we look at, we can shade in the curve to the left. If 35 are greater, so this is 35, then this is going to be 65% because the area under a curve adds up to 100%. So we want to go in our Z table and find out the value closest to 65. When we do that, that gives us a Z score of 0.39 is going to give us the closest to that. All right, if we keep looking here, we look at low birth weights for babies. The researchers in Norway looked at the births of 400,000 newborns. The distribution was normal with a mean of 3,668 grams and a standard deviation of 511 grams. Babies that weigh less than 2,500 grams at birth are classified as low birth weight. What percent of babies will be identified as low birth weight? Show your work. So again, always start with a graph. This is normally distributed with the mean 3,668 and the standard deviation 511. And their low birth weight if they have a birth weight of 2,500 or less. So we put in 2,500 here. And that's just a small amount of babies right there. So to do this, we want to find our Z-score. Again, that's value minus mean over SD. And this is for our Z-score. So we've got 2,500 minus 3,668 over our standard deviation of 511. When you calculate that, don't forget your negative. That's negative 2.29. You can look in the Z table or in your table to find that the value is 0.0110, so about 1%, which makes sense because that is such a small part of the curve. Find the quartiles of the birth weight distribution and show your work. So to find the quartiles of the birth weight distributions, what you have to do is you have to look at what the quartiles mean. So the first quartile is the 25th percentile, the third quartile is the 75th percentile. So you have to look in table A and see which values give you the closest things to that. So for 25th percentile, your Z-score is negative 0.67. And for 75%, your Z-score is 0.67. All right, so once you have those values, we have to solve backwards for our value. So if you're starting with your percentage, or your Z-score, I'm sorry, that's your value minus your mean over your standard deviation. So you have to multiply by 511 on both sides, and then add 3,668 to both sides to get X. That ends up giving us about 4,010. That's for our positive value. If we repeat the same thing with negative 0.67, we get 3,325.63. So we get that value. So those are kind of the two values that we're going to compare here and the two values that we're going to get when we look at this. All right, so we have those two there. So those are the percentiles of the birth weights. This is Q3 and this is Q1 based on that. I'm going to stop the video here if you have more questions. The answers are actually in the back of your book. So they're in that attachment on Google Classroom, I believe. But keep working, keep studying, keep practicing.